A VLAN hopping attack is going to enable traffic from one virtual local area network to be seen by another virtual local area network. And this is without the aid of a device such as a router. This is a basic VLAN hopping attack. A threat actor is going to configure a host to act just like a switch. And then using that host, they're going to take advantage of the automatic trunking port feature that's enabled by default on most switch ports. This would be the modes of dynamic auto or dynamic desirable on the switch ports. The threat actor is going to configure the host to spoof those 802.1q signaling and those DTP messages so that the trunk will form between the host and the switch. With a successful trunk established, they're going to be able to send and receive traffic on any virtual local area network, effectively hopping between any VLANs that they want to connect through. With a VLAN double tagging attack, a threat actor is going to embed a hidden 802.1q VLAN tag inside of a frame that already has an 802.1q VLAN tag. What's going to happen here is we're going to have an attacker that's going to double tag a frame. For example, our attacker was going to build a message that's going to communicate from its current VLAN, which is VLAN 10, with a targeted VLAN of VLAN 20. With the attacker currently being on VLAN 10, they're going to build a frame that's going to have an external VLAN header on it of VLAN 10, and then an internal tagged VLAN of VLAN 20. When that message is sent up to the first switch, our first switch is going to see the external outside header of VLAN 10. It's going to strip that off and then send this traffic on its way to any device running in VLAN 10. Well, the switch sees that VLAN 10 is also the native VLAN, so it's going to remove the VLAN 10 header and move it across the trunk link. Now, as that frame moves across the trunk link, the first header of VLAN 10 was removed. And now the internal tag, which is the VLAN 20, that it still exists. This second switch is going to receive that frame, and it's going to strip off that VLAN 20 header, and then it's going to forward it out any VLAN 20 ports, which includes down to that targeted host. This is effectively allowing our threat actor machine on VLAN 10 to communicate to the target on VLAN 20 using a double tag. Now, VLAN hopping and this whole idea of VLAN double tagging, they can both be prevented by putting in a couple security guidelines. Number one, we should get rid of trunking on any access port that goes to end devices. Also, the whole idea of auto trunking, using things like dynamic desirable and dynamic auto, that should be disabled. We should use a manual static trunking as needed. Also, native VLAN should only be used on trunk links, and that native VLAN should never span to a user device. For instance, in this scenario only works when the threat actor is on the same VLAN as the native VLAN between our switches. DHCP is a powerful tool for easy dynamic addressing across our networks, but it can also be a powerful tool for malicious threat actors that want to have some fun with a network. So, quick recap of DHCP. We have DHCP servers that are going to dynamically provide addressing for us. That addressing includes IP addresses, subnet mask, default gateway, DNS servers, and even more with DHCP options to our clients. The typical conversation with DHCP goes back to DORA. Discover, offer, request, acknowledge. Our client's going to send a broadcast message, which is a discover. A server is going to hear that broadcast message and respond with a unicast offer of, this is what I can give ya. Here's some addressing info. The client receives that offer, it's very excited, and it sends out a broadcast of, I accept the offer you sent me. That server finishes it up with a unicast saying, you like the offer, I'm glad, I acknowledge. And then the lease is complete regarding the client taking that addressing info. It sounds easy enough, but now let's bring in an attack. Now it sounds funny saying it, but there's two common types of DHCP attacks. We've got the DHCP starvation attack and DHCP spoofing. With DHCP starvation, the goal of the threat actor is to create a denial of service for your connecting clients. What would happen is the threat actor would gobble up all of the usable DHCP provided addresses. The easiest way to go about this is having a threat actor using a client machine that's cycling through source MAC addresses very quickly, and for each source MAC address, gobbling up an available IP address being given by your DHCP server. When all the addresses are taken from the DHCP server, there's nothing to provide the legitimate clients. On top of that, there's the DHCP spoofing attack. Imagine having a threat actor putting out their own DHCP server on your network. And when your clients use the whole DORA process and they broadcast out for a discover, and then there's the offer, the request, but then your rogue DHCP server finishes the conversation with the client with an acknowledgement providing wrong default gateway info, incorrect DNS servers, as well as even wrong IP addresses for the clients to use. Effectively, your legitimate clients cannot communicate on the network. So we have to prevent this by using safeguards and implementations for security.